it as some kind of negative work. Okay? So delta U equals to negative W. And we can try to understand by looking at the free falling object. Okay. Now, if we release some object from a height, okay, from rest, so it will be in acceleration, so the velocity of the ball will get larger and larger. So from the energy point of view, what happens is that at this point, it has some potential energy, okay? And this potential energy, so when we release it, the energy stored here, the potential energy, will accelerate the object, so it's getting faster and faster. Okay. But on the other hand, by the definition of the work, we know what happens here is that you have some object here, so there is a gravitational force here. So this gravitational force will be pulling it down, so accelerate it, so make it faster and faster. Okay. So one way is to understand it in terms of potential energy. So initially you have higher potential energy here. When it drops, the potential energy decreases. Okay. So you have some potential energy change, delta U. And on the other hand, if you try to understand this from the work, so that means there is some force, and you have some displacement, okay, along the direction of the force. So you have some work. And so the two kind of understanding should give you the same thing. So the change in the potential energy should be the negative value of the work. Okay. So this is one thing. And if you notice, if you look at this equation there, in fact, I put a C here. Okay. That says not all kinds of work can be related to the potential energy change. Only some of the work can be related to the potential energy. The work here is called WC. C means the conservative. All our forces we have so far, we can put them into two categories. One category is called the conservative force. Another category is called the non-conservative force. And only the non-conservative force, the work done by the conservative force, okay, can be related to the potential energy. The potential energy is associated with the conservative force. Now, let's look at what we mean by conservative force and the non-conservative force. Okay. So here, you can see that the example of the conservative force, spring force, gravitational force. Okay. And example of non-conservative force, frictional force, tension, and the normal force. Here we see that potential energy is only related to the conservative force. So that's why we have the spring potential energy, we have the gravitational potential energy, but we never talk about the frictional potential energy. Okay, it's impossible for us to assign some potential energy change to the work done by the spring potential energy, done by the frictional force. Now, the key difference between the conservative force and non-conservative force lies in the back here. If we try to calculate the work done by the conservative force, you'll find that the numerical value of the calculation will be independent with the path of the motion. And if you are calculating the work done by the non-conservative force, you are going to find that the numerical value of the work will depend on the path, okay, you are taking. So it's basically that for the conservative force, if you have some initial point I, final point F, if you have different paths, like say 1 and 2, okay, if it's conservative force, then W1 has to be the same as W2. Okay, the work you calculated along the path 2 and the work you calculated along the path 1. They have to be the same. Okay. And for if it's non-conservative force, initial point, final point, this is path 1 and path 2. Okay, if it's non-conservative force, then the work you calculated from path 1 will not be the same as the work calculated from path 2. Okay, so the work actually depends on the actual path you are taking. Okay. So here, what you have to pay attention to is that this kind of distinguish, how can you distinguish them is kind of not very straightforward. We are talking about conservative force and non-conservative force. But to distinguish them, you have to consider the work done by the two forces. Okay. So this is not very straightforward. Now let's look at, for example, if you try to calculate the work done by the gravitational force. Okay. So for example, if you have some object, okay, undergo some free falling from here to here, okay, or it undergoes some path, somehow you manage the path from this point to this point. If you calculate the work done by the gravitational force, you will get the same value, and you will see that it only depends on the height change. So from here to here, or along this path, it doesn't make any difference when you calculate the work. But for frictional force, for example, okay, you can see that if you have frictional force, so along this path and along this path, the work will be different because the distance, okay, of this path is longer, and the frictional force will do more work along this path. Okay. So that's a key difference between the frictional force and between the conservative force and non-conservative force. Any question here?
The example you gave right there is conservative.
Hmm?
The example free falling would be conservative.
Okay, conservative or not here, I'm talking about the force. So what I'm saying is that this example shows that if when you're considering the gravitational force, it's a conservative force. The work done by the gravitational force is independent of the path. For the same kind of system, if you have frictional force, the frictional force is the non-conservative force. So that means if you have the object from here to here, along this path or this path, your work done by the gravitational force will be the same. But the work done by the frictional force will not. Okay. But of course, if it's free falling, you don't have even frictional force. So but if you have air resistance, then you are going to see that the air resistance along this path and along this path, the work done by the air resistance will be forces, we call them non-conservative forces. Okay? Any question here? Now let's look at why we want to make this kind of distinguishment. Okay? So basically, the question is, we say that we can only define the potential energy for conservative force. So let's try to understand why we can only do it for conservative force. Why don't we define potential energy for non-conservative force? Okay. So you can see here, the point is that potential energy, to be meaningful, that means at any particular point, you can only assign a particular value for the potential energy, right? Okay, if you already choose your zero reference point. So let's think about this. Consider if you have a conservative force, and say in this case, the W1 along the path 1 equals to negative 30 joule, okay, and W2 here also negative 30 joule, okay. According to the definition of the conservative force, along any path they have to do the same work. Now I can use this fact to define the unique potential energy for each point. Right? If I say this is our 0 point for the potential energy, according to that, delta U equals to negative WC. So at the final point, the potential energy UF should be 30. Right? If U initial equals to 0. If you calculate from here, there is negative 30. So the final value for this point is 30. If you calculate from here, negative 30 and negative 30 again is 30. So no matter which path you are taking, finally you will arrive at the same answer. So there is a unique value for the final potential energy. But now if we are considering the non-conservative force, okay, in this case, for example, W1 here equals to negative 30 joule, and W2 here equals to negative 40 joule, right? And again, we set here as our U initial equals to 0. Now let's try to find UF equals to what? If we have, we say, okay, we still use that equation. According to that equation, if you can get from the path here, the first path, then UF along path 1, you are going to get UF equal to 30 joule. Along path 2, UF equals to 40 joule. Right? So then you don't even have a unique value for this point. Then this value becomes meaningless. Okay. So you cannot say, okay, what is the final potential energy for this point? 30 or 40? You cannot say anything about that. So, question?
Could you specify potential energy if you say which path you're taking?
But then, again, I say, okay, then you are talking about work. So work is always meaningful because it depends on the path. But now, when we say a potential energy, it's only meaningful if we can say, okay, at a particular point, like this point, potential energy is 30 joule. And this point, the potential energy is 20 joule. So you have to assign a one unique value for each point. But now our discussion shows that for non-conservative force, you cannot use this unique assignment of the numerical value. Okay? When you calculate the work, and if you try to convert it to potential energy, you're going to get different value for a particular point. Okay? In fact, you can get infinite number of non-points here because they have infinite possible paths. Okay? So then we cannot assign the potential energy for non-conservative force. But of course, we can still talk about the work. Question?
What if on the first one, if it was, for the first path, it was positive 30 joules, and the second one, work 2 is negative 30 joules. Is that still UF is equal to 30? Or
No, it cannot be. Okay, here value for the work has to be completely the same, including the sign. Okay. If this is negative 30, this is positive 30, that means it's not conservative force. It must be some kind of non-conservative force. Along all the passes, you will get exactly the same value for conservative force. Okay. Another question? Okay, this part is quite kind of confusing, but you have to think about carefully. Later we're going to talk about the application of these things. Now, okay, now let's do some calculation to help us